Welcome back. In this video, I wanted to spend some time talking about the effect that random molecular motion has on particles in nanosystems. And so the particular phenomenon we want to talk about, or that I want to tell you about, is called Brownian motion. And Brownian motion was first observed by a botanist named Robert Brown. That's where the name comes from, and he was interested in, among other things, pollen. And so he spent a lot of time looking at pollen suspended in solution. And what he noticed was when he looked very closely at grains of pollen that were suspended in liquid, and so these pollen grains would have had a diameter of something on the order of 50 microns or so, maybe smaller. When he looked at these grains of pollen, what he noticed is that they were not absolutely still. They actually vibrated and wiggled, and they moved all around, and they were never ever still. And he noticed that large grains tended to move much slower than small grains, and the large grains tended to vibrate a lot less than the small ones. And so he explored this phenomenon, and that's why the phenomenon bears his name today. But basically what he was observing is the random thermal motion of particles, and the thermal motion of particles drives their movement at the nanoscale, at the microscale and the nanoscale. So what I want you to do is think about a box. So let's imagine we have a box here, and we're going to fill it full of water, and we're going to put a divider in the middle of the box, a removable door. And in one half of the box, I'm going to fill it full of red dye. So these are red dye molecules. And if I were to just watch this box, what I would see is random molecular motion of all of these particles. They would be bouncing around and constantly jiggling around. If I turn the temperature up, they would actually move a little faster, and if I turn the temperature down, they would be a little slower. So what I want to do is make a plot here of my concentration, a plot of my concentration versus position. So I have my position along the x-axis, so the x-axis represents the width of the box. And on the y-axis, I have concentration. And the concentration is going to be normalized so that it can have a value between 0 and 1. And this is where the divider is going to be. So the divider sits here. And if I plot the concentration, my graph would look something like this. It's 0. There are no dye molecules until I get to the divider. And then once I get to the divider and head on over to the right wall, it's complete molecules. So no dye molecules, I hit the divider, and then a uniform concentration of dye molecules all within this box. So this is at time 0. Now what I want to do is I'm going to pull the divider out and watch what happens. Okay, so I remove the divider, and then I sit back and see what's going on. What I'll notice is that my molecules are jiggling around, but what happens is they start to jiggle over to the left. So they're gradually migrating. There's still a lot more over here on the right than on the left-hand side, but there is an overall net motion of these molecules to the left. And if I draw my graph of what's going on, it would look something like this. And then 1 and 0. So if I plotted this, it would look something, it's going to have kind of an S shape, a sigmoidal curve shape. And so a couple of things. Here, the concentration has started to increase a little bit, and here the concentration has started to decrease a little bit. So this is greater than 0 now, and this is a little less than 0. And in the middle region, what's happening is as the molecules move to the left, I get sort of this sigmoidal shape. And then if I wait long enough, what happens is I get molecules evenly spread throughout. So this is T equals T2. And this is a really long time. I go to eat lunch and I come back, and what I see is dye molecules evenly spread all throughout my volume. Now, they're moving around randomly this whole time. They're bouncing around. They're still jiggling around because they still have thermal energy, thermal motion. But if I plot my concentration graph, it looks something like this. Nice flat line, nice and even. Everything is nice and mixed. I have a uniform concentration of 1/2. And so simply by removing the divider, what I've been able to do is generate molecular motion. All right? So I have a net flux, even though each of these molecules is moving randomly, right? Each of the molecules has Brownian motion. Right? So each molecule is jiggling individually and in a random direction, but the interesting thing is that from this random motion comes actually a net flux. So I get a net flux from the high concentration to the low concentration. Right? So I get a net flux of molecules. Oops. I get a net flux of molecules from the right-hand side, from the high concentration, over to the left-hand side, so in the direction of the blue arrow. This net flux is known as Fick's law, and it's written J equals minus D dC dx. So J is the term for flux, so that's the amount of molecules per unit area. And then dC is the difference in concentration. And dx is the distance over which that difference in concentration exists. This capital D is something called the diffusion coefficient, and we're going to talk about this a little more in a minute. All right? Okay, so even though each molecule is randomly moving, it's randomly jiggling around, right? So I have a molecule and it's bouncing around and going randomly in different directions. I can still extract from this, I can calculate a distance d that I think it's going to travel in a certain amount of time. And this relationship was first deduced and proven by Einstein, and the equation for this is d squared equals 2dt. Okay, so lowercase d is the average distance that I think my particle is going to travel, so the average distance over a certain amount of time. Capital D is the diffusion coefficient. And then T is time. All right. So the amount of distance that my particle travels, lowercase d, is equal to the square root of 2 dt is another way to write the equation, and sometimes is how you'll see it written. So if I want to know how far my dye molecule is going to travel, I need to know this capital D, and I need to give it a time for how long I'm predicting this. Okay, at the nanoscale, these two features become very important. At the nanoscale and nanochannels in particular, these two features become significant. D is typically very small, lowercase d, because we're talking about nanometer distances as opposed to meters and so forth. And capital D, the diffusion coefficient, is typically very small for small objects. So in other words, the smaller my molecules are, the smaller this quantity. The smaller this quantity, the faster something will diffuse a given distance. This capital D, the diffusion coefficient, it's a function of temperature, right? So temperature impacts what this value is. And how do I find it? Well, there's two ways. I can either measure it, I can set up an experimental setup to measure it, or I look it up in a table. And especially now with the internet and the ready availability of lots of data, it's very easy to find the diffusion coefficient for many types of different molecules. All right, so let's see how this works in practice. Let's look at an example real quick. If I can write this without getting it on the page line. Okay. Okay, so let's look at an example. So let's assume we have a 200 nanometer diameter nanoparticle. What we want to know is how long does it take for a 200 nanometer diameter nanoparticle to diffuse 1,000 nanometers. So assume we have a nano channel, and we want to know, we have a particle and we know it's going to diffuse, and we want to know how long it takes to diffuse 1,000 nanometers. All right. Well, the first piece of information we need to know is we need to know D. So I'll give you a D for this, and it's a pretty reasonable D. Assume our diffusion coefficient for our particle is 2.15 times 10 to the minus 8 centimeters squared per second. So we'll assume that. Then what kind of time am I looking at? How long is it going to take? Well, if I rearrange my equation, my Einstein equation, I get T is equal to D squared over 2 times D. And if I plug in 1,000 nanometers squared in the numerator, and then 2 times the diffusion coefficient in the denominator, and I do my math, I go plug it in the calculator, I get 0.233 seconds. Okay? So in other words, it takes a nanoparticle, 200 nanometers in diameter, about 1/4 of a second, or a little over 200 milliseconds, to go from one side of the channel to the other. So literally in the blink of an eye. And this is very representative of the times that one sees at the nanoscale. You see diffusion rapidly takes particles across nanometer distances. And so at the nanoscale, Brownian motion, and diffusion in particular, so diffusion moves particles quickly. It moves very small particles relatively quickly over relatively short distances. So it is a significant force that you need to consider when you're analyzing your systems. So let's take a look at another example real quick. And I want to take this same system but change the distance. So let's change our distance instead of 1,000 nanometers. Let's see how long it would take our nanoparticle to diffuse 5 centimeters. All right, so several orders of magnitude greater distance. Okay, so if I put, and in this case, let's assume it's a beaker. So I've got my beaker here. I fill it full of water, and I put my dye molecule up here. and I want to know approximately how long is it going to take my particle to go that 5 centimeters. Well, if I do my math again, and now I plug 5 centimeters squared into the numerator, and then in my denominator I still have my d of 2.15 times 10 to the minus 8th. Right? If I plug those numbers in here, I get a very large number. I get 5.8 times 10 to the 8 seconds. Okay, so times 10 to the 8 seconds. So in other words, 580 million seconds. That's a lot of seconds. And in fact, if you convert this to years, this is 18 years. So it would take 18 years for diffusion to move a 200 nanometer particle a distance of 5 centimeters. So as the distances become large, diffusion becomes less and less important. So again, the take-home message, diffusion moves particles quickly at the nanoscale, and it's a significant factor of these types of systems. All right, so let's talk a little bit about the diffusion coefficient D. And how you actually calculate it. So I said before, you look it up in a table or you measure it, but you can actually calculate it as well. And you use an equation known as the Stokes-Einstein equation. The Stokes-Einstein equation, and it looks like this. So k times t over mu times 6 times pi times r. And in this equation, k is the Boltzmann constant. T is the temperature. Mu is the viscosity of the fluid that the particle is in. And r is the particle radius. All right. So you can see that the diffusion coefficient is a function of temperature and viscosity. These are both significant factors in calculating the diffusion coefficient of a particle. So what are some example diffusion coefficients that you might run into? Well, some examples are an ion. So let's say you have a potassium ion floating around in solution. You've dissolved some potassium chloride in water. Then a reasonable diffusion coefficient for this would be 2 times 10 to the minus 5th centimeters squared per second. Right? So then what about a glucose molecule? So a molecule of glucose is a ring-shaped structure. So it's got several atoms, made of several atoms to form a molecule of glucose. So it's much larger than just a single ion. So because it's larger, its radius is larger. So we would expect a slightly lower diffusion coefficient. And indeed, you see that. So the diffusion coefficient for glucose is about an order of magnitude lower. Right? And if we keep going down, we look at a fairly large biological molecule, hemoglobin. And hemoglobin is a very large protein, and it's made of many, many atoms. It has a molecular weight of tens of thousands of kilodaltons. It's quite large. We see, in fact, it's about 10 times slower than glucose. And lastly, what if we get into the nanoparticles? So these length scales are on the order of angstroms. And then hemoglobin is approaching nanometer length scales. So what about an actual nanometer length scale? We could look at something like a virus particle. So viruses have dimensions that are on the order of nanometers typically. And they're shaped like rods or even little hexagons with bodies. Right? A virus particle is going to have something like, yet again, another order of magnitude slower. Right? So you can see the diffusion coefficient, it's very common for a diffusion coefficient to jump by a factor of 10 or more as your molecules become larger. So the diffusion coefficient can rapidly become very, very slow. Virus particles are on the order of nanometers, so this is the regime that we were in calculating our diffusion time. So if you go back and look at that beaker example, where we calculated the time it would take for our nanoparticle to go from the top to the bottom, it would take a virus particle about 10 to the minus, it would take a virus particle about 18 years to diffuse that distance as well. All right? And so the take-home story, one, is that Brownian motion is important for nanoparticles and nanoscale systems. So nanoscale systems. And two, the second thing is that the nanoscale dimensions, the nanoparticles and nanochannels we're talking about are at sort of the upper limit for where this is true. So we are right at the boundary, or the border, if you will, where diffusion is a significant mechanism. Any much larger than nanoscale objects and diffusion and Brownian motion start to become less and less important.